Thank you very much for letting me speak about this and inviting me to talk to you about the water cycle. To tell you what I'm going to tell you, I'm going to review some theory behind GPS reflections. I believe I've met the rule of having no equations. Then I'm going to move right into some results for PBO H2O, which some of you know is our snow, vegetation growth, and soil moisture. But when Adrian contacted me about coming today, I said I wanted to talk about some new things. So I'm going to end up with some new things I've been working on. So basically, this is my one picture view of how GPS does its thing for PBO. We have GPS receivers that are measuring the distances between the satellites and the antenna. And we have a complicated modeling problem of calculating orbits and the clocks on the satellites. And we have to correct for atmospheric delays and relativity and the receiver's clock. But at the end of the day, we estimate position once per day, once per week. And we pretend that ground reflections don't matter. And I would say from this point on, I'm not going to talk about regular geodesy. Instead, if you want to measure water cycle parameters with GPS, it's the same system. GPS is transmitting at the same frequencies, same everything, except that I'm going to use something different called signal strength data. Just think about every piece of electronic equipment you have. Your cell phone's telling you it has a signal strength, right? That doesn't really tell you what people are saying into your ear, but someone's measuring signal strength. GPS receivers do the same thing. And of course, in my world, ground reflections are good. So that's what Megan was talking about my love for noisy data. I will only say in my own defense that my colleagues would like me to move every PBO antenna that looks like this. They'd like me to rotate it toward the ground. So, it could be worse, combining these networks. So I want to show you what signal strength data look like. It's different than GPS data if you're used to looking at ranges. But this is one satellite track. The units are different because I'm measuring power of some kind. This is a rising satellite. That's the setting satellite. When I talk about the direct signal, I'm talking about the boring part of the signal that's measuring all those vectors for you. That's the part of the signal that goes right to the antenna, if my head is the antenna. That's the part you use to measure X, Y, and Z. But of course, you see these oscillations there, right? There's big as day, and those are caused by ground reflections. That's what in geodesy we ignore. So if I take out the direct signal and I just isolate those signals, this is what I get. This is what it looks like. This is the rising part of the satellite signal. I've got some kind of power signal. And you see these very nice, oscillations. Where do those come from? Well, they're basically just coming from geometry. It's not that hard. Basically, you have a plane wave. Are yours funny? No, I guess, all right, they look okay, I guess. So the direct signal here goes right to the antenna. This signal, everything's even up till the dotted line. Then it travels this additional distance in red. So all I'm talking about is the fact that the reflected signal travels a slightly longer distance. Sometimes that direct and reflected signal are out of phase completely and you get nothing. Sometimes they're close to each other. Sometimes they're off by 45 degrees. You have an interference pattern that's generated by the interference of the direct and reflected. That's it. Okay? Where does the frequency of that interference pattern come from? This height of the antenna. That's it. The height of the antenna and the signal wavelength. I tried to put what I do into one page. So basically, if there's a reflection off bare soil, that's sort of my zero boring thing I do. Okay? Bare soil, that's boring. If I add a snow layer, you can see that my antenna is closer to my reflecting area, right? So H has changed. This is bare soil. Now there's snow, so H is smaller. It changes the frequency. So the dotted line has a different frequency than the black line. If I add vegetation, what I'm doing is basically adding water all over the ground, because nice vegetation has water in it. Water slows down my reflection, so the amplitude of my reflection goes down. It doesn't really change the frequency because I'm still hitting the soil, but I've been slowed down along the way. And it's hard to explain why soil moisture does this, but basically if it rains and you just have a tiny little bit of soil moisture change, there's a small phase shift. So that's my representation of that. Why would anybody care? Basically, it's kind of funny. Soil moisture is the one most people care about. Climate scientists really want to know how that water cycle works when you have rain, how much stays in the soil, how much evaporates out, how much is available for vegetation. It's really important for understanding climate. Snow, if you're from the western US, you know that we need the water in the mountains to run our farms and for our daily living. And we hear about carbon modeling all the time. So that's another part of what you use the water cycle studies for, is to study biomass, what's called biomass. Okay, so I talked here 2 years ago, and I had an idea. I don't think I'd even written the proposal yet, but the idea was to take some of this theory that I showed you 2 years ago and turn it into an operational network. I think if I had to explain it, it's basically I use the exact same data files that you all use to create position and vectors, and I turn them into 3 products: snow depth, vegetation, vegetation water content, and soil moisture. So we went public right before the election. These products are updated daily. We start downloading data, I think, the evening as soon as the UTC day ends, and then we post the solutions. I think, when I'm drinking coffee, that's when I like to have my new products available. So they're available around 7 or 8 in the morning. And I'm just going to show you some examples, and then I'll move to the new things. So I'm not going to show you everything. This is one of my favorite sites in eastern Idaho, P360. Got to show a movie. Basically, we were looking for a relatively cheap way to validate our data, and it makes for a nice movie. So basically, I'm going to show you pictures. We took a picture of this post every day, and then we're going to digitize the snow level by looking at this post. But at the same time, I'm going to show you our GPS estimates of snow depth. So down below, Kristine measuring snow depth. Up above, you get to see the snow showing up in the picture. And I can't do an animation to save my life, but that we had a great web guy do. You can see that, sure enough, Kristine says snow goes up. The picture says snow goes up. This is the comparison of when one of my undergrads digitized the camera photos. So what you see is a very good agreement on when things go up and down. You don't see perfect agreement. There shouldn't be perfect agreement. The GPS technique is measuring about 1,000 square meters around the antenna, because I'm looking at satellites all over the sky. I ain't looking at satellites that rise and set on that pole. That pole is going to give me one number, but it's a good number to compare to. Why do the climate people like this? They want to see the variability. So now we have 4 years of data for this site, and you can see that sometimes the snow is higher, sometimes it's lower, sometimes it melts earlier. Why do people need to know this? Not just so we can drink it and use it for our lawns, but to find out whether there's going to be a flood if it melts too quickly. So that's why these data are useful. So I'm going to skip my ridge. And I'm going to go to plants. The joke here is, what a great network to study vegetation of the San Andreas Fault. Did we not do a great job? Anyway. All right, what do plant scientists want to know? I did not know this before I worked in this field. Basically, they have this thing called green up, which you can figure out what that is. Senescence is a fancy word for death. Peak growth is what it sounds like. And the main thing that this community uses is called NDVI. Just think of it as an optical remote sensing satellite data that measures color. And not just any color, green. It measures greenness. So when NDVI values are high, when they're 1, they're green, and when they're 0, it's white. That correlates with chlorophyll, which tells them something about plants. Of course, it's optical, so it doesn't work in clouds, and you don't get a product every day. GPS, we don't care about clouds because we're a military system that was designed to work in bad weather. We are sensitive to water in the plants, not water in the air, the same way. And we have data every day, so I'm going to show you, I apologize, a site in eastern Wyoming. I like it. I like that the NDVI correlates very nice with the GPS. I like this because there are 2 peaks. But I'm just going to focus here. In the middle panel, we show the 5-year average in black of precipitation, and then I show that year's precipitation. So this was a high water year average, a little high, a little high, a little high. Then this is like horrible, horrible last year. And you can see that it was deathly hot and low precipitation last year. In 2012, the vegetation never grew. Why? It was 10 degrees Celsius hotter for April and May, and basically you can see the precipitation levels in 2012. Not only did it not snow, it basically never rained. So if you lived in the middle of the country, you know about this. And then let me quickly show some California things that I think are kind of neat. And then, well, no, I'll skip California. All right. Soil moisture is, as I've said, it's the hardest thing to do. I measure soil moisture only in the top couple inches. That has to do with the fact that GPS is L-band. Because really, hydrologists, I was talking to someone in the break, they want to know soil moisture levels at multiple depths. They just don't want to know at the top. But these people are needy, and they'll take the top if they can get it. So I'm going to give them the top, which is this blue thing that when it rains, it gets very wet, and it dries pretty quickly. If you're down 20, 25 centimeters, you're pretty much the same water level all the time, unless you're in drought. Why would people want to know? The reason these people need GPS is because SMAP is a L-band mission NASA is launching. L-band, I'm L-band, we're both measuring the same region. So it's a good validation tool, and of course, we can provide the data to the Drought Monitoring Bureau. Oops, there's my results. So it looks like soil moisture. So that's the key, is that when there's precipitation, soil moisture goes up, then there's this drying cycle, and that's what we use to tell the climate scientists what's going on. So I've been talking to you about SNR data and using SNR data, and clearly I've been focusing on these oscillations, and some of you have seen my talks before. I've spent maybe 3 or 4 years working on these oscillations. This year I'm on sabbatical, so my brain had a little time. And I thought, well, what about these data? These are the boring data that the positioning community uses. But so basically, these are the data above your head when there aren't any obstructions and you don't get any reflections, right? Well, but what if there is an obstruction? What could there be? And I want to thank the people at Alaska for, just motivating this part of it. Well, that looks like an obstruction. What about a signal that went through an ash cloud? And Ronnie has some results that are impressive. They've already come out where he looked at some things with it, and I looked at it a slightly different way. This is Mount Redoubt, and this is just the geometry. Jeff and Ronnie had a station here. We know where it was. If you go to Wikipedia, you know where Mount Redoubt is. And there happened to be a satellite, and Ronnie identified it in his paper. We know where the satellite is, so I know that I know where I'm intersecting a plume. Now, I can't tell you the ash here versus the ash here. I get an integrated plume effect. So what does that look like? Well, these are the SNR data that I said were boring. This is the day of the eruption. This is when the seismologists say the eruption happened. This is 2.5 hours of SNR data. 2 days before the eruption, day before, day after, day two. So you can see that the SNR data are really boring, but that's helpful because it tells you this is special. It tells you you're going through an ash cloud, which means not all the signal's getting to the antenna. You've been obstructed. This is what it looks like if you focus in on it. And then more or less for fun, I looked at these papers. What do these guys do? They calculate the plume ascent rate. I wanted to be like everybody else. So I figured, well, I know H from the geometry I showed you. I know the detection time because this is when things kind of first showed something. And then I'm going to calculate my plume speed, and I'm going to compare it to some USGS results. USGS results that were done for 19 eruptions of Mount Redoubt. And what they're showing here is time after eruption start and altitude, which is giving you an ascent rate, that vary between 25 meters per second and 60 meters per second for those 19 events. And this is the GPS value. So you can see that even though the SNR data, are kind of throwaway data for most people, here it gives you a very clear view. You went through a plume, you know which satellite track it is, and you have something you're measuring that's telling you signal strength that you can relate through models to ash density. So that's the take-home message. Other obstructions, I think this is from a USGS professional paper, probably on Mount St. Helens. So that's kind of an obstruction too, right? I got crap on my antenna there. Why would that be important? And I think this is no surprise to people that work with Alaskan data. I mean, just everything in Alaska is, just harder. These are the data that you can pick up from PBO for this particular site in the northeast and up direction. And, it's either a very exciting place or it's got a lot of crap on its antenna. So I would say it's got a lot of crap on its antenna. So what I'm going to do here, you know, for the volcanic plume, I looked at a specific time. But here I'm going to just take an average every day of the boring data. So every day I'm going to compute what's the SNR level above my head, and then I'm going to plot it. And this would be what normal SNR data look like. You might be horrified by the time dependence, but that's a good thing. It tells you your instrument is working. Cold GPS receivers have less noise than hot GPS receivers, basically. And that's why your SNR levels are higher in the winter than they are in the summer. So this would be, you know, you see it varies from, you know, about 45 to 46.5. That's a good GPS receiver. This is a crappy SNR time series. It's for AV29, the Alaskan site. And it really requires very little development of algorithms to identify this is when the antenna is covered with ice or snow. I'm now not being obstructed by ash, I'm being obstructed by ice in this particular case. It can also be from snow if the snow levels are high. So this paper's in JGR, and I have some code that could be distributed to the community. Okay. Okay, and the other thing I want to say is some people, not everybody, but some people clean up their time series by basically fitting a line, and they say, well, we know plate tectonics are linear, fit a line, everything that doesn't look like a line we throw out. With SNR data, you don't have to assume it's a line, that it's geophysically linear. So it's a different physical principle, so I think it's superior to assuming that. So this is with using SNR, you can produce a cleaner time series. So I want to end up, I'm almost on, I'm like on time. It's amazing. For the last 9 months, I've been working on a project, and I was talking to John Tabor. He's like, why did you do all this? And I'm like, I don't know, I get a little obsessive. But I have this idea that we should tell people about all the cool things you can do with GPS. And I think Chuck Meertens and I have been talking about this for years. But so we did it. And it, you know, we were funded by Greg. I think I told Greg I was doing this as part of my education and outreach, but it's really, it's about all of GPS. It's not about water cycle products. So let that be understood. We took it off the water cycle portal almost immediately because we didn't want it to be just about us, but we're there too. So, so we have a section on how GPS works. We have a section on GPS and tectonics, and we have a section on water cycle products. I'm perfectly willing to add more squares. Pretty sure I want to keep it on high precision geoscience applications, but like polar science, atmospheric science, those are the kind of things that could get their own square. And my target audience is 8th to 12th graders, really. I mean, 12th saying maybe first year college students could benefit from this in an intro or science background thing. So we also have, in addition to this background content, we have spotlight sites. Yeah, I've already gotten unhappy Alaskans that I made them a tab rather than, you know, making Alaska show up. You know, let's just think later it'll be the world. Right now it's the Western US, and you have to click up here to get Alaska. So I had scientists volunteer to help me spotlight these GPS sites. So I'm going to spotlight my absolute favorite, which is Sally McGill. She did a San Andreas Fault spotlight. The data are there. It's uploaded every week. There's a picture of, every site has a picture, a map. The scientist is supposed to provide images. Sally's were spectacular in that I thought she did a good job of making them at the right level. They were interesting. She also had pictures with people, you know, things like that. So she knows how to get people's attention, I think. I'm set up to create positioning plots every week using the official products. You don't have to do anything. I can make your maps. In this case, she's, of course, comparing 612 and 610 because you can't study a fault with only one station. And then we have spotlight questions. So each scientist was asked to come up with some questions for kids to answer. And then we added this section about, you know, why did you become a scientist? What's your job like? And what do you hope to learn from your research? So I would love to have more sites in the Western US. I would love to add more sites in the Eastern US. Ultimately, though, I would like to, you know, expand this to the world, but let's do one thing at a time. But if you are interested, please let me know. And then I'll just stop and give you some conclusions. We produce water cycle products every day. We validate our results mostly in publications if possible. We are hoping to encourage some of you guys to get into this business if you are geodesists. But also I have been doing a lot of outreach to the climate community to get them to assimilate our data. We are also building sensors where we can point the antenna toward the ground, which is the cheaper way to do it. I do have these other things, and they will be available soon. And I think that's it.